Hello, class. In this lesson, we're going to learn about the tangent-secant theorem and the interior case for the secant angle theorem. So the tangent-secant theorem says that when we have an angle formed by a tangent and a secant segment that has an endpoint that is the point of tangency, this angle has to have half the measure of this intercepted arc. So we're going to go about proving that. And to do it, we want to draw in triangle ABC. And now, what can we say about the measure of angle BAC? Well, it's a central angle, so it has to have the same measure as its intercepted arc, so it also measures b degrees. And what about angle ABG? What's its measure? Well, that's formed by a radius and a tangent here, so that has to be 90 degrees. And what do we know about the other two angles in this triangle? Well, this is an isosceles triangle, right? Because these are radii. So we know the base angles have to be congruent. So those have the same measure. And we know that this base angle plus its measure plus 8 degrees has to give us 90 degrees, right? Because they're complementary. So if you write that in terms of our base angle, we can say that it's 90 minus 8 degrees. And now if we combine our three angles, using what we know about the interior angles of triangles, what equation can we write? Well, we have b plus 90 minus a plus another 90 minus a. That has to equal 180 degrees. And if we solve this for b, the constants end up canceling out, and we get b equals 2a. And if we divide both sides by 2, multiply both sides by 1/2, we end up with what we wanted. This says that a is half of b. So this is very similar to what we already learned about inscribed angles. So let's apply this. What's the measure of angle 1 here? Well, by our tangent-secant theorem, it's going to be half of 130 degrees, so 65 degrees. And for major arc KJL, it's going to be double the measure of that angle, so 250 degrees. Here we have a theorem that says that when we have an inscribed angle and an angle forms like in the tangent-secant theorem that have the same intercepted arc, then those angles have to have the same measure. They're congruent. So let's see how we can prove this. Well, we know BEA, its measure is half of the measure of this intercepted arc BFA. And we know from the tangent-secant theorem that the measure of angle BAD is half of the measure of that same arc. So these are both equal to the same thing. So we can say by substitution or by transitivity in this case as well, that these are the same measure. So let's apply what we've learned, try to figure out the measures of A, B, and C, and then I'll show you my solutions. So for A, if we look at its intercepted arc, over here in yellow, that's the same arc intercepted by this angle here that measures 34 degrees, and that's formed by a tangent and the secant segment that has an endpoint on the point of tangency B. So we know that they're congruent by that previous theorem, so that's also 34 degrees. And what can we say about angle EDB, this angle right here? Well, that's 90 degrees by Thales' theorem, right? This is the diameter. So we know that A and B are complementary, so that must be 56 degrees. And for angle C, let's look at its intercepted arc. So that intercepts this green arc, but so does the inscribed angle DCB. So since these are both inscribed angles with the same intercepted arc, they have to be congruent, so they have the same measure. So when we have two secants to a circle, there are a few different scenarios that can occur when we're talking about their intersection. So take a look at the four diagrams here and see if you can describe the differences between them. Well, in the first diagram, the secants intersect inside the circle. Here they intersect on the circle. In the third one, they intersect outside the circle. And in this last one, they don't intersect at all. They're parallel. We're going to spend the remainder of this lesson looking at the first scenario, when they intersect inside the circle. So we want to figure out what the value of x is. And if you notice, the angle here, BGE, which measures x, G is its vertex, but it's not the center of the circle, and it's not an inscribed angle. So we can't directly apply those properties. But what we can do is we can connect B to D. And then we end up with two inscribed angles. And what will their measures be? Well, their intercepted arcs are 40 and 120. So since they're inscribed, you take half of those. So this one is 20 degrees, and this one is 60 degrees. And if you notice, BGE is an exterior angle to this triangle. So we know its measure must be the sum of the two remote interior angles. So its measure is 80 degrees. And what do you notice about the measure of x and these two arcs? Well, x is 80 degrees, and that's half the sum of these two arcs, right? 120 plus 140 is 160 divided by 2 is 80. And we want to show that that result holds in general. So here, we've replaced those measurements with a and b. You don't know what the measures of the arcs are. And what do we want to say about x? How is it related to these two quantities? We want to say x is what we get if we add a and b together and divide by 2. So let's go about it the same way as before. Connect b and d. And what can we say about the measures of these two angles? Remember, G is not the center, but we have inscribed angles here. So the measure of GBD is half of A, because that's the intercepted arc, and the other one is half of B. And since x degrees, that's an exterior angle measurement of that triangle, that has to be the sum of these two amounts. And we simplify it, and we get A plus B divided by 2. And how can we describe this with a complete sentence? There's lots of ways to describe this result, and here's one of them. So we have just proved the interior case for the secant angle theorem. So when you have secants that intersect inside the circle, if you're looking for the measure of the angle they form, or one of the angles they form, we know these are vertical, so they're the same, you just take the sum of the two intersected arcs and divide it by 2. So take a moment to apply this property to this problem. So try to solve this on your own, and then I'll show you my solution. So x is formed by these two secant segments, and we have these intercepted arcs, so it has to be the sum of them divided by 2. So 150 plus 80 divided by 2. So that's 230 divided by 2, which gives us 115. And for y, well, this is a segment, right? So we know that these are supplementary. So 180 minus 115 gives us 65. Now this one is still the same theorem we're applying, but slightly different way to solve it. So let's see, how do we figure out what x is first? Well, this is supplementary to the angle that measures 121 degrees. So x is 59. Now, if we apply our theorem, well, we know what x is, but we don't know what one of the intercepted arcs is. So 59 is equal to the sum of y plus 42 divided by 2. So we don't know what this arc is, but we can solve for that using some algebra. There's lots of ways to solve this. I multiplied both sides by 2 here. So we end up with this equation. And so now we just got to subtract 42 from both sides, and we end up with 76. In this lesson, we learned about the tangent secant theorem and the interior case of the secant angle theorem. Thank you for watching this video.